This meeting is being recorded.
Hello, can you hear me?
Yep.
Yeah. Yeah, I think people are joining, so we wait for 1 minute and then we can start.
Okay. Is my audio okay?
Yes, yes.
Okay, good.
Okay.
Shall I
welcome.
share my screen?
Yes, yes. So you have roughly 50 minutes for the talk and then some time for the questions.
Yep.
Yeah. So welcome you all to the second CMB Bharat Cosmology Seminar Series. So I'm pleased to introduce Professor Eiichiro Komatsu as our seminar speaker from Max Planck Institute of Astrophysics, Garching. So Professor Eiichiro is a well-known figure in cosmology community. He obtained his doctoral degree from Tohoku University in Japan in 2001. While working on his doctoral thesis, he joined the WMAP science team at Princeton, where he later did his postdoc. So Komatsu joined the University of Texas at Austin in 2003 as a faculty member and then became a director of Texas Cosmology Center. In 2004, he received the Young Astronomer Award from the Astronomical Society of Japan for his work on constraining inflation models of the early universe. And in 2010, the Nishinomiya-Yukawa Memorial Prize for Physics for his study of early universe, as well as several other awards and fellowship. So currently, he is a director of Department of Physical Cosmology, Max Planck Institute of Astrophysics in Garching. So he will talk about parity violation in cosmology. The floor is yours. So, Eiichiro,
Okay, thank you. Yeah, thank you for the introduction. Thank you all for joining this call. So I'll be happy to talk about parity violation in cosmology. So the overarching theme is we want to understand our cosmological model. So one thing I wanted to point out is that we have a standard cosmological model, flat lambda CDM, and each word, actually each letter even, flat lambda C D M is a new physics. So we don't know why universe is flat. We don't know what the lambda is. We don't know if we don't know the origin of M matter. We don't know what D is, or whether it's actually dark or not. And certainly we don't know whether it's cold or warm, right? So there are a lot of ideas about these unknown components in standard cosmological model. And I wanted to tell you that perhaps parity is the new hint that we can use to understand fundamental physics behind flat or lambda or C or D or M. Okay. And I wrote a review article on this back in 2022 in Nature Reviews Physics, so you can take a look at it. You can also look at the archive. Basically, the focus here is the cosmic microwave background. Polarization is sensitive to parity, and the new component in this article is a parity symmetry and violation of it in a cosmological context. So I hope you enjoy reading about it. If you like it so much, like I do, I can also point you to this page where, so basically last year I went to Nagoya University. It's a center of Japan, right in between Tokyo and Kyoto. With bullet train, Shinkansen is very easy to get there from either Kyoto or Tokyo. Nice place. I gave 7 lectures on parity violation in cosmology, 85 minutes each. So as you can see, this topic can be quite rich, and there are a lot of things in there. So I hope you enjoy learning about this new subject in cosmology. Now, of course, parity itself isn't new. It's a well-known concept in particle physics. So let's say parity transformation is the inversion of all spatial coordinates, not just x or y or z. It's all of x and y and z. And parity symmetry states laws of physics are invariant under inversion of all spatial coordinates. But I wanted to point out immediately that you shouldn't be really bothered by coordinates, because we all learn that coordinates are just labels the humans came up with. Nature doesn't care about the coordinates. Certainly, my body, like a ball, when I throw a ball, it will follow the parabolic trajectory regardless of what coordinate system I use. Nature doesn't care. My momentum exists regardless of how I chart the universe. So coordinates are not important, but another deep thing we learned over the years is coordinate transformation. So when you go from one coordinate to another and watch how physical systems appear differently in these 2 coordinate systems when you compare the 2 coordinates, this can be useful. Right? It's not essential to have this kind of thing, but it's sometimes useful to watch how physical system changes when you change coordinate systems. Very good example is Amy Noether's celebrated theorem. She said, when space has, so when physical system has translation symmetry in 3-dimensional space, so physics doesn't change whether you shift the coordinates by constant. If the system is invariant under coordinate translation, then linear momentum is conserved. So that's a very deep statement one can make about the nature by simply stating how physical system changes when you change the coordinate system. Yeah. Similarly, when the physical system is invariant under 3-dimensional rotation, the angular momentum is conserved. So there's a deep connection between coordinate transformation and the underlying physics. Parity is a discrete symmetry, unlike translation or rotation. So it does not come with a conserved charge. But once again, parity can be useful to study. And we have lots of examples like that. So the concrete question I ask is, when we observe a certain phenomenon in nature, do we also observe its mirror image with equal probability? So when I observe certain phenomenon in right-handed coordinate system, do I observe the same phenomena in left-handed coordinate with equal probability? Okay, that's the question. So let me just give you an example. So this is this is not cricket. This is softball or baseball, if that term is more familiar to you. So in Munich, sunny day, Sunday, we play this softball, and then basically, so this batter is me, so I just hit the ball, right? And I just went to the parabolic trajectory, and I run in one direction. Now I'm going to flip the coordinate, just one coordinate, so it's not the full parity, but just one coordinate is flipped. Then question is, can you tell whether this is a mirror image or original image. If you cannot tell if this is the original or the mirror image, then laws of physics underlining the softball is invariant under parity. Yeah, but if you can tell that this is certainly mirror, not the original, then the softball rules are not invariant under parity. So here we go. All right. So because this isn't cricket, I think cricket is more or less parity invariant actually. But so let me explain. Okay. So first of all, unlike many of you, so these players are mostly Japanese. Japanese people are right-handed. So when you see that people wear gloves on the left hand, they are right-handed. So this pitcher is right-handed, right? He throws the ball by right hand, right? And then I am a right-handed hitter in this case. So in this image, people are all right-handed, and here they are all left-handed. So you may wonder, right, what's going on? But maybe that, if you didn't know, maybe Japanese are actually predominantly left-handed, right? So you cannot tell maybe. Another thing you can try is the gravity. So this ball forms a parabolic trajectory in both frames, original and mirror image. So gravity is invariant under parity. By simply following the trajectory of the ball, you cannot tell whether this is original or not. However, if you know anything about baseball, here you know that I'm running in this direction, yeah? And I keep running like this. In this image, I'm running the opposite direction. So it has a wrong-handedness, you see? So when you knew anything about baseball, this is the moment where you know that this is not the original frame. This is the mirror image, and this does not occur in nature with equal probability, okay? Therefore, you can say immediately that this image has wrong-handedness, therefore parity is violated. Yeah, so that's the name of the game. Now, parity and rotation are different things because three rotation has the unit determinant +1, whereas the parity flips all the spatial coordinates, so it has the determinant of -1. And let's try to do the parity. So I have right-handed coordinate. Actually, from your point of view, maybe it looks like left-handed. You see? So then I try to do the parity by single hand. You can try, but you immediately realize that you cannot do it. This is, no matter how much rotation I perform by hand, that's a rotation, not parity. So immediately you realize that it's essential to go from right-handed coordinate system to left-handed coordinate system. You have to change handedness if you wanted to do any parity. So you just flip the one coordinate, then flipping of other coordinates can be done by 180-degree rotation, okay? So one flipping coordinate followed by 180-degree rotation is a full parity transformation. So if the nature is not invariant under parity, then it means that the physical system cares about whether you are left-handed or right-handed. Yeah, so universe distinguishes between left and right. Let's take a look at the vector, like momentum. So momentum vector here can be written in terms of components of the vector and the basis vector. As I said, momentum exists regardless of coordinates I choose. So P is the same in any coordinate systems, but components are different because that depends on coordinate system you chose. So in this one coordinate system, I chose EX, EY, EZ, basis vectors. In the flipped coordinate, I have primes here, and components are also primed. But I know that because this is a parity inversion of the previous one, EX prime is a minus EX, EY prime is a minus EY, and so on. And as promised, a vector doesn't care about the coordinate system. They must be equal in both coordinate systems. So that immediately tells you that px prime is equal to minus px and so on. So the components of a vector would pick up a minus sign when you do the parity inversion. Pseudo vector or an axial vector, on the other hand, like angular momentum, is the r cross p. And both r, position vector, and p, momentum vector, are vectors, not axial vectors, not pseudo vectors. And because both are vectors, both components of both vectors will change sign under parity flip. But because angular momentum is a product of these two vectors, components of the angular momentum wouldn't change in parity flip. So this is a very important difference between pseudo vector like momentum, angular momentum, and a vector like momentum. And this will tell you how to test parity symmetry in nature. The key is to form a pseudo scalar from your observables. You perform any experiments, you just find a combination of observables that will form a pseudo scalar. So pseudo scalar is like a scalar which remains invariant under three-dimensional rotation, but scalar doesn't change sign under parity, whereas pseudo scalar changes sign under parity. An example is a product of linear momentum and angular momentum. Let's say I have two particles, A and B. I measure momentum of a particle A. I measure an angular momentum of a particle B. I have a dot product. This changes sign under parity because P is vector, L is angular momentum, axial vector, right? Then I repeat this measurements all many times and measure the average of PA dot LB. Because this changes sign under parity flip, if the parity is conserved in this physics, average value of PA dot LB should be 0 because plus of PA dot LB and minus of PA dot LB will occur with equal probability in nature. Easy. And of course, that's exactly what was done in 1957. So 1956, Young and Lee basically asked the question, is the weak interaction, is the parity symmetry respected in the weak interaction? They looked at the literature and they could not find any experimental evidence that parity symmetry is respected in the weak interaction. So they suggested in the theory paper, Lee and Yang, 1956, how you might test this in the weak interaction. Then Wu and her collaborators did exactly that and reported that the parity is violated in the weak interaction. So what they did is they have a cobalt-60 with a nuclear spin pointing towards some direction. So they have a magnetic field to align spins of cobalt-60. So they knew what the J, this nuclear spin, is. Then they measure momenta of electrons as a decay products. For example, in this case, left hand, PE dot J is minus. If parity is respected in weak interaction, they should see this J dot P plus with equal probability. But to their surprise, P dot J was negative, like with very, very statistically significant. So right there you go. Pseudo-scalar's average was not 0. So parity symmetry is violated in the beta decay. Big surprise. So surprising that nobody believed it in the physical community. For example, when Wolfgang Pauli saw 1956 paper by Lee and Yang, he said he doesn't believe it, right? The God is not weak left-hander. Actually, no one believed it. Then Wu discovered it. And Pauli said, how sure are we? I mean, you hear this even today, right? So whenever somebody proposed an idea that was counterintuitive, it will be immediately dismissed. You've seen this in conferences. A young theorist goes to the podium, presents her or his new theory, then people just dismiss it. Like a senior scientist in the audience say, this is nonsense, go away. You've seen this, okay? And when somebody reported an exciting experimental evidence for new physics, completely unexpected. And they were like, this must be systematics. How sure are we? You know, this cannot be true, okay? You've seen this. So history repeats, and nowadays, okay, so I'm talking about parity violation in cosmology. If you ask any cosmologist in any conferences, they will tell you, of course, parity symmetry is respected in cosmology. They will say you. That may be true, okay? That can certainly be true. Except no one has looked at it. So my philosophy as a scientist, I've spent all my career so far testing fundamental hypotheses in cosmology. I just have to look before I conclude anything. I don't want to regret not seeing it, okay, before I retire. So, so basically, that's what I do, and I'm quite inspired by this history of Yang, Li, and Wu, and how people didn't take it seriously. Okay? Because this you see every day in the physics community. Okay, so what is a pseudoscalar I'm going to use? One pseudoscalar I'm going to use is the helicity. So let's say you have massless spin 1 particles, photons, massless spin 2 particles, gravitons, and you have direction of the momentum, and you have a direction of the spin, and you make a dot product, and then that's a helicity. And because these particles are massless, you cannot find a Lorentz frame where this helicity can change sign. There's no inertial frame for, there's no raster frame for photons or gravitons. So when photon has a positive helicity in one frame, it will always have positive helicity in other frames, okay? Now let me do the parity transformation of helicity. Okay, let's say I have this. So my thumb is going in the direction of momentum, and my rest of the fingers representing the spin, so rotation, let's say. In this case, spin is going in this way. I mean, this is tricky because to me, this is right-handed, but to you, this is left-handed, right? So here, let's say. Then I do the parity transformation. So first, I flip x-axis, okay? So momentum in z direction didn't change, but the rotation in x direction changed. But then this is not the parity yet, okay? We have to rotate by 180 degrees. So the momentum are now opposite, but rotation, you see, the direction of the rotation didn't change. This is tricky to do in Zoom. Yeah, you see? Rotate in the same way. So this tells you that angular momentum or spin angular momentum are pseudo vector, momentum are vector. Yeah. So under parity flip, helicity changes. So if you see any asymmetry between two helicity states, plus or minus, you see the sign of the parity violation. Okay. So let's talk about parity violation in electromagnetism. Maxwell's equations. These equations are invariant under Poincare transformation, so spatial rotation, translation, and Lorentz boost. It is also parity invariant if you insist that electric field is a vector, magnetic field is a pseudo vector, charge density is a scalar, current is a vector. So if we ever detected a magnetic monopole, that would be pseudo scalar for these equations to be parity invariant. So Maxwell equations, as we all know and love, are invariant under parity inversion. Now let me put this into the familiar forms, covariant forms. So here's the sourced part of the Maxwell's equation, this one. This is a source-free part of the Maxwell equation. That's the thing. F mu nu, everyone knows. Dual tensor, I will define later, but this basically represents this second equation. That's F mu nu, okay? Then let's make a square of it, F mu nu. F mu nu, that's magnetic field square minus electric field square. So although B and E have opposite parity, square has the same parity, namely parity even. So this F square is a scalar, and it's invariant under parity transformation. On the other hand, this dual tensor, F tilde, is basically you have F and an anti-symmetric Levi-Civita symbol there. That's F dual. And basically it has the like a dual property, not, instead of E here you have B, instead of B here you have E. And for the kind of definition of dual tensor, when you dot this dual tensor with the original tensor, it's a pseudo scalar. So B dot E changes sign under the parity. So this FF dual is a pseudo scalar, and this FF dual has a name like a Chern-Pontryagin intensity. So these two, and however, you probably haven't really seen this FF dual in your life before, because you don't learn this in your electromagnetism class, because you don't need it. You can derive all the Maxwell equations from the action given by F square and a vector potential dot the current. Because source-free part, divergence of F dual is a Bianchi identity. It's true regardless of the dynamics. It's just given by the definition of F, Bianchi identity. So you don't need action for it. But the question is, can we add still this Chern-Pontryagin density, FF dual, to the action? And answer is certainly yes. There's nothing wrong with it. You can add scalar or pseudo-scalar to the action, fine. Except this is a surface term because FF dual is a total derivative. So it just drops out when you integrate. It's a surface term. So that's why you don't talk about it. However, you can tweak. So if you multiply this FF dual by dynamical field, theta, then you can do integration by parts, and you pick up this derivative, space-time derivative of a field theta. This doesn't have to vanish, okay? And this has a name. So when you write this derivative of theta as a generic 4 vector, P mu, then you can P mu, A nu, F tilde mu nu. You then take mu equals 0, okay, mu equals 0. So this is actually, can be written just in terms of 3-dimensional components and derivatives. This is known as Chern-Simons 3 form. So this is, once you integrate this over 3 volume, this is the topological invariant. So this was discovered in mathematics by Chern and Simons in 1974, but this even appeared previously in the standard model, pion. So pion, neutral pion decays into 2 photons exactly via this term. Theta is a pion in this case. So theta is a pion divided by so-called decay constant. So decay constant determines the lifetime of pion. That's 184 megaelectron volt. Lifetime is a pion is 10 to the minus 18 seconds. So in 10 to the minus 18 seconds, neutral pion decays into 2 photons. And coupling constant alpha here is an electromagnetic fine structure constant times order unity. So it's 10 to the minus 2. Okay. So this is the ABJ anomaly, 1969. And in fact, this term, theta FF tilde, or P mu F A nu F nu tilde, has been discovered 4 times in the history of physics. 1969, the ABJ anomaly. 1974, Chern-Simons 3 form, that was only in 3 dimensions, actually odd dimensions, 1, 3, 5, 7, odd dimensions, this Chern-Simons P form. But this was then promoted to four-dimensional theory by Carol Field and Jackie in 1990. Equivalence principle was used to derive this equation completely independently of anything else like this, 1977. And then axion electrodynamics by Pierre Sikivi in 1983. So in other words, this term is not a strange thing. Existence of this is confirmed in standard theory, and it is very well motivated. So basically, what I'm asking is, what if this theta field is dark matter or dark energy, or maybe was active during inflation? Okay. Now let's go back to this form here. P mu a nu f mu tilde, like a Chern-Simons form. Because A, right, is a gauge field, and if you want to maintain gauge invariance of electromagnetism, then you have to make sure that the action is invariant under the gauge transformation like this one. This then suggests, due to Bianchi identity, that antisymmetric derivative of P mu is 0. Okay. There are two ways this can happen. One is P is a constant. So it's like you have a constant vector, 4-vector in the universe. This will be the maximal violation of Lorentz invariance in the universe. That's fun to look at, okay? Doesn't have to be the case, but it's a fun possibility. Another is a P mu is a gradient of a dynamical scalar field, such as this one, okay? So both possibilities exist. Another interesting possibility recently put forward was that, okay, maybe this P mu is the fermion current. But if you say that, it breaks gauge invariance. But then you add another field, like a Stuckerberg term, to restore gauge invariance. That's still physics beyond the standard model. But if you do that trick, then this can be it doesn't have to be constant or gradient of a scalar, but can still be also fermion current, for example. So many possibilities exist, and that's very interesting. But in this talk, basically, I asked whether theta is a dark matter or dark energy or active during inflation. And I talked about abelian gauge field, like electromagnetic field, but it doesn't have to be abelian. Can be non-abelian, SU2. Can be even gravitational fields, Riemann field. Or you can have both. You can have everything and have lots of fun. Okay? So let's correct Maxwell's equations. That's a new Maxwell's equation. Let's go to the vacuum. So J mu is 0. And I write down the usual propagation equation for the spatial vector potential. That's that. As promised, you get this correction term. Okay? Now, it's not obvious if you look at it whether parity is violated. So let me go to the helicity state, because as promised, helicity is a useful thing if you wanted to talk about parity. Instead of having A1, A2, A3 in Cartesian coordinate like this, I rotate them so that I have the complex combination of helicity plus and helicity minus. If you do that, then that's the equation. If I assume for simplicity, I don't have to assume this, but for simplicity, assume theta is homogeneous, so it doesn't have the spatial term, okay? Then you see that dispersion relation, so propagation of photons suddenly depends on helicity. So that's the indication of parity violation. Good. So what happens? Let's imagine that you have electromagnetic waves propagating in vacuum filled with a field chi, which can be dark matter or dark energy. Okay. Alpha is still a fine structure constant. F is a new decay constant. That's no longer 184 mega electron volt, because I don't want dark energy or dark matter to decay into 2 seconds. F has to be big. And there's only an upper bound Planck mass, a lower bound such that decay time is much longer than the age of the universe. And this chi field doesn't have to be a fundamental field. It can be composite, like pion. Pion is a pseudoscalar field, but of course it makes up, it's made of quark and antiquark. So just like that, your dark matter or dark energy field can be a composite field. That's perfectly fine. Okay, then what do I mean by dark matter or dark energy? So when I have a scalar field in the potential and it oscillates, that's dark matter, because if you compute pressure over density of the oscillating scalar field, that oscillates, and if I take the time average, it's 0. Okay, so time average pressure being 0 is the pressureless matter, so it's basically equivalent of dark matter. But if I have the field still rolling down on the potential slowly, then this ratio is -1. That's dark energy. Dividing point is if the mass of this field is less than the current Hubble's constant, so 10 to the minus 33 electron volt in natural units, then this still behaves like a dark energy because it hasn't started oscillating even today. If mass is greater than this, then dark matter, this behaves like a dark matter today. It might have been like dark energy in the past, but today it is dark matter. Okay, so that's the difference. Then I have this effective frequency square, which now suddenly depends on the helicity state. Okay, so photons propagating in a vacuum coupled to dark matter or dark energy via Chern-Simons term, they depend on helicity states, and this phase velocity omega divided by k now depends on the helicity states. So circular polarization states propagate differently with different phase velocities. Then if you assume that this first term is much greater than the second term, you can use WKB approximation. You get this plane wave solution. And C plus minus is the initial amplitude. So if the initial light was already circularly polarized, C plus and C minus will be different. But let me assume that initially it was not circularly polarized. Omega second term is much less than first term for the present day universe. Therefore, I can ignore the second term in the amplitude, which means this effect does not generate new circular polarization if initial light was not circularly polarized, but I keep this second term in the phase. Then when you compute the polarization, linear polarization of this, you can convince yourself that the plane of linear polarization rotates by some angle beta given by the difference between omega plus and omega minus, integrated over time. Because I have to take the difference between two numbers here, I shouldn't ignore the second term, even if it is small, because the leading order term vanishes. Then you get the final result that the angle of the rotation of the plane of linear polarization is given by difference between field values of the dark matter or dark energy at emission of the light and observation of the light. Let's test this, okay? So let's use CMB. CMB was emitted a long time ago, 14 billion years ago. And when it was last scattered by electrons at the last scattering surface, it was polarized. Take CMB Bharat is going to measure this, right? If Indian funding agency is kind enough to fund this space concept. But then we typically assume that linear polarization state of the CMB hasn't changed over 14 billion years. But if you had this coupling between dark matter and dark energy and photons in Chern-Simons term, this polarization plane will be rotated. This is familiar. It is similar to birefringence effect in crystal. So if you shoot a laser polarized, in sapphire, the polarization will be rotated. So we call this cosmic birefringence. The space filled with dark matter or dark energy parity violating, behaves as if it were a crystal. And if you detect that rotation, it's a sign of parity violation. Okay. Let's find the pseudoscalar, because whenever you want to do the parity violation search, you have to form a pseudoscalar. Okay. So I decompose this CME polarization pattern into E modes and B modes that are eigenstates of parity. Because E and B modes have different parity, if I multiply the two, EB correlation is a pseudoscalar. I take the full sky average of E dot B. If it vanishes over the full sky average, parity is preserved. If it's not zero, then parity is broken. So let's take a look. So parity eigenstate, this is the polarization fields, and then you can decompose this E and B, which have opposite parity transformation properties. Here, take the square of E polarization, CLEE power spectrum, that's scalar. B square is also scalar. Temperature E mode cross correlation is also scalar. So none of these is sensitive to parity. Only TB and EB are pseudoscalars. So we should use those. And over the last 30 years, we have measured CMB temperature power spectrum, E mode power spectrum, B mode power spectrum. All of these are scalars. And I bet most of you have seen, I bet most of you have not seen TB or EB. So here's EB. This is the EB measured over full sky from WMAP and Planck. And I compute chi-square. So there are 72 data points. Chi-square is 125 with respect to no. It's terrible. Okay. Is it due to galaxy because we don't mask galaxy so much? No, it's not due to galaxy. You cut the galaxy a lot, still the same. Okay. So EB is there a lot. So what can be causing this? If we have this cosmic birefringence, then polarization plane will rotate it by an angle beta. This will mix E and B polarization. It does not generate anything, but it will mix E and B. So E plus minus IB observed will be equal to E plus minus IB emitted times this phase factor. So observed E and B will depend on intrinsic E and B. And even if the intrinsic B was zero, the first term is not zero. Therefore, EB observed will be intrinsic EE times tangent for beta. Yeah. So in fact, you don't have to worry about intrinsic things because there's enough information here to write down observed EE in terms of observed EE and observed BB. And we have observed EE and BB. And turns out that EE is much greater than BB. So you can use this to probe beta. Okay? It's very nice that EE is much greater than BB. If EE and BB were equal, we will never be able to do this. Okay? So we are very lucky that EE was much greater than BB. So you see that because EE is much bigger than BB and EE has these distinct acoustic oscillations, you can look for it. So you can fit this observed EB to EE minus BB. And fit is beautiful. Now chi-square is 66 for 71 degrees of freedom. It's a beautiful fit. It's a 9 sigma detection of beta. Is it due to galaxy? No, it is not. You can also try different masks and you get same answer. Okay. So this is not due to foreground. Foreground doesn't have acoustic oscillation. Okay. Okay, good. What is it? The biggest problem is not foreground, but the miscalibration of detectors. So basically, we so far interpreted this rotation of angle by cosmological signal. But if you rotate your telescope, it creates the same effect. So you have to know very precisely the orientation of polarization you detect and how it is related to the orientation in the sky. If the polarization is rotated by your optical system, lenses, telescopes, detectors, all of them can rotate your polarization plane. Then you screw up, right? You cannot do this measurement. Therefore, basically, you can only measure without, in the absence of any other information, cosmic birefringence angle and your instrument miscalibration angle alpha. So that's why if you look at the literature, there are many, many different numbers. For example, 2016, Planck had 6 sigma positive detection. Paul Rabier had 3 sigma detection, but minus sign. So SPT is 15 sigma, but twice as big, and ACT something else. So the limitation is that we don't know what alpha is. That's why we cannot really convert this into actual value of beta. So that seemed like a dead end, but we solved this issue in 2019 by realizing that Milky Way is polarized, and Milky Way polarization came from only 10,000 light years away. There was not enough time for polarization to be rotated by dark matter or dark energy. It's right there. It's in our backyard. Unlike CMB, which traveled for 14 billion years. So basically, our idea is if you detect rotation of a polarization of the Milky Way emission, it has to be alpha and by not beta. So using that, we were able to recalibrate both WMAP and Planck. Because both missions ended already, you cannot just go and then recalibrate them. And to our satisfaction, our recalibrated angles are completely consistent with laboratory measurements. So WMAP measured polarization absolute angles in a lab, and that was good to within 1.5 degrees. Planck to within 1 degree, and all of the answers we got were comfortably consistent with lab experiments, and we made it better. So we recalibrated the instruments. Yeah. And then now we are decomposing 9 sigma signal into 2 components. One is miscalibration angle, alpha, that's red here, and cosmic birefringence, that's blue. And green is the best fit. Now, because we're decomposing 9 sigma into 2 components, that's no longer 9 sigma, it's 3.6 sigma. It's a beautiful fit. Is it due to Milky Way? No. You get the same answer. Of course, error bar gets bigger because we rely on foreground. If you cut the foreground, we lose sensitivity. So, as simple as that. But we still have, 2 sigma, even if you cut the sky aggressively. And what is it? So going back to electromagnetism course, we also learned that if you have a magnetic field parallel to your line of sight, then photons polarization will be rotated. It's a Faraday rotation. You can also define the polarization rotation angle beta. However, Faraday rotation depends on photon frequency. If you have high frequency photon, effect is smaller. So this beta will be proportional to 1 nova frequency squared. So I wanted to do phenomenological fit, saying beta is frequency to the nth power. For Faraday rotation, n is minus 2, but we didn't find it. It's very nicely consistent with 0, just as was predicted by dark matter, dark energy coupled to photons via Chern-Simons-Stern. So what is it really? Is it caused by non-cosmological effects? All I can say, with a lot of work with the collaborators, we can conclude that no instrumental effects of W, no instrumental effects of Planck, known properties of foreground cannot explain our measurement. However, unknown unknowns can never be excluded unless we have independent measurements done by independent experiments done with independent methods that do not rely on galactic foreground, carried out by independent groups. For example, biceps 3 collaboration is doing exactly that. Atacama Cosmology Group is doing exactly that. And Simon's Observatory Group is doing exactly that. So none of these groups are relying on foreground, so they are trying to calibrate the instruments better. So we will see what they report. Okay, until then, jury is out, and it's only 3.6 sigma. I'm old enough to know that 3.6 sigma can disappear. Okay. But if it is due to cosmological birefringence, then implication is, first, if it is due to dark energy, it's not cosmological constant because it has to be dynamical. So cosmological constant will be ruled out. Number one. Number two, if it's due to dark matter, at least a fraction of dark matter violates parity symmetry. But frankly, would you be surprised? Because weak interaction violates parity. Why can't dark matter violate parity? To me, it would be odd if it doesn't violate parity, right? So in other words, this kind of effect is totally expected. And if you put our measurements in here, implication is field value changed by the decay constant because alpha is n-2. So that's completely natural parameter space. And so everything seems fit within kind of expectation. Now let me switch the subject and quickly mention other possibilities. So was chi active during inflation? So in this case, chi is not dark matter, chi is not dark energy, chi is some field that might have existed during inflation. And this E and B are no longer photons because during inflation, that was well before electroweak phase transition. There weren't any photons. So you just have massless spin one fields, okay? Then these Chern-Simons terms will give you a term that modifies equation motion for scalar fluctuations. And via the stress energy tensor, these parity violating E and B fields create gravitational waves. So we talked about here until now, we now talk about inflation. Then, okay, what is inflation? So I can summarize the research over 40 years. Inflation is a period of accelerated expansion, and quantum mechanically scalar fluctuations are generated. That's the origin of galaxies, stars, planets, and ourselves. Tensor modes, gravitational waves, that's the target of many existing and future CMB missions, including CMB Bharat, let's say, yet to be discovered. Vector modes, we don't know. The magnetic fields maybe came from inflation, we don't know. But these are standard law, it's a standard paradigm. A new paradigm is a source of contribution from gauge field during inflation. So that's the full model. You have inflation action that we don't know, no one understands. I have the gravitational action that gives you scalar the gravitational waves. And then rest matter sector will give you stress energy tensor. Scalar action will give you scalar fluctuation equation motion that's now sourced by E dot B term here. Then this will give you equation motion for vector field, gauge field, that's parity violating. So this will generate parity violating A, which source scalar fluctuations via equation motion and gravitational wave via stress energy tensor. That's it. Super simple. And it doesn't have to be U1 gauge fields. You can have non-abelian gauge fields, and lots of exciting things happen. And a qualitatively new thing is that if this is a spin one field, and you respect isotropy, you don't want to break isotropy of the universe, then this E and B has to be a fluctuation. So EJ is a quadratic in fluctuations. It's non-Gaussian. If E and B are Gaussian, E square or E dot B are highly non-Gaussian. So this will give you parity violating, highly non-Gaussian contributions to both gravitational waves and scalar fluctuations. Yeah? So I have this equation motion, same equation motion as before, but now, unlike previously, like birefringence, where the second term here was much smaller than the first term, peculiarity of inflation is that it can take a wavelength of fluctuation and stretch it to super horizon size. This does not happen in late time universe, but inflation, this can happen. When that happens, this second term can be bigger than the first term. And if you pick up minus sign due to helicity, then this omega square can be negative. So you have imaginary frequency. That's an exponential amplification of one of the helicity states. So you get very, very parity violating, completely helical spin one fields during inflation, which will source completely parity violating, non-Gaussian and scale-dependent scalar perturbations. Now you can simulate this. You put this into the simulation box and generate inflation and large scale structure in CMB, and also gravitational waves, not only scalar. Yeah. So therefore, you can have, for example, power spectrum of spin 1, spin 2. Helicity plus 2, helicity minus 2 power spectra have these terms which are parity violating. So this is the same for both plus and minus states. That's vacuum contribution. That's the source contribution, and that's much bigger for plus state than the minus state. Yeah, so it's parity violating. And this can be observed. So here we're talking about CMB, but primordial gravitational waves exist at all wavelengths, not just light world, and not just CMB Bharat, not just CMB. You can have pulsar timing array, you can have LISA, you can have Einstein telescopes, and these gravitational waves are completely circularly polarized. So that's something you can look at. And experimental strategies so far, and I wonder if the CMB Bharat is assuming the same thing. If we detect B-mode polarization that looks like a primordial gravitational wave, so far our strategy was to check for black body spectrum, frequency spectrum. If it's black body, we go to the next question. Is it scaling independent? Okay. Is the B-mode power spectrum consistent with scale invariant gravitational wave? If the answer is yes, you claim a victory and you announce the big discovery of the vacuum fluctuation in space-time. If not, you're confused. I propose to change this. We changed that. First, we of course have to check for Planck spectrum, then scale invariance. Then we have to test for parity violation, and we also have to test for Gaussianity. And once all of these are checked, no parity violation, no non-Gaussianity, no non-scale invariance, then you claim a victory and say you detected vacuum fluctuation in space-time. If not, you discover something even more exciting. It's a particle, it's a gauge fields or some exotic matter fields during inflation. This opens up completely new research area of particle physics in Toshita space. So I like this better because if you just measure vacuum fluctuation, it's Gaussian, scale invariant, no parity violation, it's just dead end. That's the end of the era. Okay, no more information. You cannot make progress. But if you have non-Gaussianity, parity violation, and non-scale invariance, there are lots you can learn. So I end here and take questions. Thank you very much.
Thank you. Thanks for the wonderful talk. So it's very crystal clear. So if from the audience, if you have question, just raise hand. Yeah, Devabhadra. Devabhadra, you can unmute yourself and ask.
Is he muted? Well, can I? I'm asked to click view. Should I click on this? No. Oh, he's not muted, but somehow he cannot speak. Huh?
Yeah, maybe
Can
someone.
you type in?
Yes.
Can you Yeah, type in chat maybe. Then I can come back to that question.
Yeah. Others? Fazlu?
Hi, am I audible?
Yes.
Yeah, okay. So my question is like, if the non-zero detection of birefringence, so if you believe that it is coming from the dark matter, and does it, okay, so does it give a strong belief for us to think that dark matter is made up of axions instead of WIM kind of thing?
So let's say, thank you for the question. So there's one constraint. So let's say if it is dark matter, then you would start oscillating after or during or after recombination time. So that's redshift and that's a field value.
Yeah.
And if it's still not oscillating today, that's dark energy. So that's mass less than 10 minus 32 electron volts, black line, that's mass. But if the field was oscillating well before recombination, we don't see it in CMB. So we will be oscillating during or after recombination. So that means mass will be less than 10 to the minus 28 electron volts. That's quite light. Yeah.
Yeah.
We know from observations of larger scale structure in CMB that such small mass axion cannot be 100% dark matter. It will be 1 to 2% at most of the total dark matter. So if this birefringence is due to dark matter, we know at least a fraction of dark matter is parity violating, but we cannot make a statement of the rest. However, axion is like a cockroach. If you find one, there are many. So the theoretical people predict that there's a mass spectrum of axions. So there are a lot of axion fields with different masses. So if we confirm that the birefringence is due to dark matter with the mass of 10 to the minus 28, this will motivate people to look everywhere in mass. And the people have been traditionally looking at masses of micro electron volt, but not so much else. So this suddenly opens up the possibility to look for 10 to the minus 20, 10 to the minus 10, 10 to the minus 8, everywhere. So I think that would be the implication, and I think that implication will be a lot of fun. Of course, we can still have WIMP, but just knowing that axion exists somewhere in some parameter space, just knowing that will be very useful, in my opinion.
Okay, thank you.
There is a question in the chat. So without measuring the primordial B modes, how can we find EB and use it for testing parity violation?
Yes, yes. So there are two ways that parity can be violated. One is parity can be violated in primordial way. Another is a parity can be violated as photons propagate. It's a later time effect. This here. Okay. So if polarization is rotated by later time effect, even if there's no detection of BB, okay, EB can still be given by EE. So, and also it's a bit like, because E is so large, EB is much easier to measure than BB. For example, TE was much easier to measure than EE. So for that reason, we don't need to detect BB before we do science with EB. And indeed, that's exactly what's happening. So, well, maybe it's a bit really different because BB was detected, okay? But here, the EB that we measure is somewhere here, this magnitude. Yeah.
Yeah.
So we don't really have to detect BB before we talk about EB. However, there's a second answer to your question, namely, how can we distinguish between parity violation later time and parity violation early time? Because I said that gauge fields during inflation can violate parity, and that will give you circularly polarized gravitational wave. So that's a B-mode polarization of gravitational wave. And when you have EB coming from parity violating gravitational wave, EB power spectrum looks like B power spectrum. Okay. Whereas birefringence will look like scalar E mode. So primordial EB will be like this. Birefringence EB like this. So you can distinguish them very cleanly by the shape of the EB power spectrum.
Okay. There is another question. If dust has intrinsic EB correlation for some reason, can we use this to break the degeneracy between calibration error and cosmic rotation?
That's more or less what we did. So actually, it's, I think, okay, so that's basically what we did. So in fact, but maybe I should answer you because you're an expert. I should answer this well. So here, I said, if I see EB of the foreground emission, then I said this is due to miscalibration, not causing birefringence. Now, your question goes beyond that. What if EB already existed in foreground before miscalibration? And that possibility has to be taken into account. And that's included in the fitting. So, this, so this also contributes to breaking degeneracy between calibration error and cosmic rotation, yes. So both effects should be taken into account. EB intrinsic and EB due to the miscalibration.
Okay. There's one question by Vishnesh. Vishnesh, you can unmute yourself.
Hi, can you hear me?
Yes.
Yes.
Yeah, thank you for the nice talk. So I had a question about the error bars. So in the EB power spectrum that you show, right? Yeah. So
Yes, yeah.
yeah, so we seem to have very large error bars right now. So do we have an idea of how much we expect these error bars to shrink in the upcoming experiments, like
Oh yeah, so LightBird will measure everything up until here. By the way, minimum multiple here is 50. LightBird will measure, and also CMB Bharat, right? From L of 2 to L of few hundred, because it's a space mission with small aperture. So angular resolution is about half a degree. So beat down error bar, like these one, to very, very small values. Okay? But then rest, these high multiples, will be improved massively by Atacama Cosmology Telescope, South Pole Telescope, Simon's Observatory, and eventually CMBS-4. So these error bars will be tiny. And so I think the future prospect is quite good.
Thank you.
Oh, of course, signal may not survive until LightBird flies. Signal may be gone by then, but if it is confirmed by, so ACT is going to announce DL6 this year, hopefully. BICEP 3 will also announce something this year, hopefully. And then next year onward will be Simon's Observatory, CCAT, and then 10 years from now will be CMBS-4 and LightBird. And maybe CMB Bharat, so we'll see.
Okay. More questions?
If I am audible, then I can ask follow-up question. Can you hear me?
Yes.
Oh, sorry. My question was, if you have already EB dust correlation for some reason, like your modified black body is getting summed up due to different properties along your line of sight of dust clouds, so that can give you the distortions in the polarization angle. Or if your dust grains are misaligned in your multiphase ISM phases, that can also give rise to the distortion in the polarization angle. So in this case, you have the three angles, like the one is the cosmic birefringence, one is the distortion for the dust, another is the miscalibration angle. So
Yes.
two of these three affects the CMB, two of these three affects the dust. Then how can you break the degeneracy between the calibration and the cosmic birefringence?
Because the calibration angle is multiple independent, whereas the dust effect has multiple dependence in angle. But I mean, if we are very unlucky, we may not have the multiple dependence for dust either. But basically, multiple dependence can be used to distinguish. You can keep talking until I find the appropriate slide that makes that point. Let's see. No, I might actually have it here. Hold on. Here, okay? So we have intrinsic foreground EB. Then I model EB by dust TB, dust TE, and dust EE. And then you can formulate this by the multiple dependent new angle gamma. So this is the angle you are talking about, right? Dust rotation, yeah. So this can include decorrelation effects, like you say, this line of sight effect or intrinsic dust EB. Then you can basically model this using observed TB dust, TE dust, right? And all these things. So that's your gamma. And A is a free amplitude. So you fit for this in large multiple bins to the data simultaneously to alpha. Then you can disentangle between these two effects.
But this correlation between this EB, EE and BB is true only if our knowledge is right about the misalignment of dust grains in the magnetic field, right? But it doesn't.
Well, that's one model. That's one model. So this model gives rise to this model here. So this physical picture gives you this. But I think this is much more generic. But basically, how do you relate EB? Because TB is parity violating. If you see TB, you expect EB with the same sign. Why? Because this relationship is quite generic, right? So basically, TB and TE defines one angle, EE defines the amplitude, and then you fit this with free amplitude, and that's EB. So I think this is quite generic. But as you said, this misalignment is one realization of this phenomenon. Yeah.
Thanks.
Yeah, I have one question about this EB power spectrum. Then you compute. So you're computing from the mass sky, or you compute from the full sky and then you mask the EB spectrum?
We first mask and then measure TB
Okay.
from the masked sky.
Okay.
And then, yeah, you basically all these computed from different masks.
Okay.
And that will give you different EB prediction for different masks.
Okay. Okay. So I don't see any raised hand. So let's thank for the. So from all the audience, I'm just thanking you for the nice, beautiful talk.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thanks. Bye.